I want you to picture a collection of points on a line. It's infinitely packed together, totally dense, and yet it has no size. And I don't mean its size is 0 or infinity. I mean its size is literally undefinable. Today, we're going to dive into one of the absolute strangest things in all of mathematics, a set that completely shatters our intuition about how we measure anything.
So let's just ask it straight up. Can a set of points really have no size? I mean, that sounds impossible, right? It has to be something. Well, stick with me because by the end of this, you'll not only know the answer is a resounding yes, but you'll see exactly why it's so logically necessary. All right, so to understand how something can break the rules of size, we first got to agree on what those rules are. And back in the early 1900s, a brilliant mathematician named Henri Lebesgue basically took our common sense ideas about length and built a rock-solid system around them. It's called the Lebesgue measure.
And look, these rules are super intuitive. They're things you already know. Rule 1, the length of a line segment from point A to point B. It's just B minus A. Simple. Rule 2, if you take a set and just slide it down the number line without stretching it, its size doesn't change. That's called translation invariance. Makes perfect sense. And rule 3, if you've got a bunch of separate pieces that don't overlap, the total size is just what you get when you add up the size of each piece. We call that countable additivity. These 3 ideas are the bedrock of how we think about size.
But here's the thing. Lebesgue, the guy who made the system, left this huge question just hanging in the air. He wondered, is it even possible to dream up a set of numbers that you just can't assign a size to? A set that would break one of these common sense rules if you tried? He couldn't find one, but the question was officially out there. So to even begin to answer Lebesgue's question, mathematicians had to reach for a really weird and powerful new tool. It's one of the most debated ideas in all of math, and it's called the axiom of choice. The philosopher Bertrand Russell came up with the perfect analogy for this. Imagine you have a warehouse with an infinite number of pairs of shoes. If I ask you to pick one shoe from each pair, that's easy. You just make a rule. I'll always take the left shoe. Done. But now, imagine the warehouse has an infinite number of pairs of socks. They're identical. There's no left sock or right sock. There's no rule you can state that tells you which one to grab. You just have to choose. And that's all the axiom of choice really is. It's a guarantee. It says that even if you can't write down a specific rule, the act of choosing one item from each of an infinite number of bins is always a mathematically valid move. It lets you make an infinite number of arbitrary choices all at once. So armed with this powerful, controversial new axiom, the stage was set. And in 1905, just 3 years after Lebesgue asked his question, an Italian mathematician named Giuseppe Vitali stepped up and used it to construct the very monster everyone was wondering about. Okay, the way he built this thing is just genius. Here's how it works. Step 1, take all the real numbers between 0 and 1, the whole interval. Step 2, we're going to sort every single one of those numbers into an infinite number of imaginary boxes. The sorting rule is this. 2 numbers go in the same box if you can subtract them and get a rational number, a simple fraction. Step 3, and this is the magic trick, we use the axiom of choice. We reach into every single one of those infinite boxes all at once, and we pull out exactly one number to be the representative for that box. And finally, step 4, we take all those representatives we just picked, and we gather them all together into one new set. We'll call it V, the Vitali set. So we've built our weird little set V. Now what? What happens when we try to apply those 3 simple rules of size to it? Well, as you're about to see, the whole system just short circuits. It leads to a complete, inescapable contradiction. Let's start with a thought experiment. Let's just assume for a second that our set V is measurable. We'll pretend it has a size, a length. We can call that size lambda of V. Maybe that size is 0, maybe it's something bigger, but let's just assume it's a number we can define. Now for the fun part. We take our set V and we make a whole bunch of copies of it, a countably infinite number of copies to be exact. Each copy is just the original set V, slid up or down the number line by a different rational number. And because of our second rule, translation invariance, every single one of these copies has to have the exact same size as the original, lambda of V. Now here is where it gets totally mind-bending. Because of the clever way we built V in the first place, these infinite copies do 2 incredible things. First, none of them overlap, not even by a single point. They are completely separate. And second, if you take all of them and put them together, they perfectly fill in every single gap in the interval from 0 to 1.
And at the same time, the whole collection of them fits neatly inside the larger interval from -1 to 2. So think about what that means. Because all our copies together contain the entire interval from 0 to 1, their total size has to be at least 1. And because the whole collection fits inside the interval from -1 to 2, which has a length of 3, their total size has to be less than or equal to 3. So we're trapped, right? The total size is stuck somewhere between 1 and 3.
This is where the paradox just smacks us in the face. Remember Rule 3, countable additivity. The total size is the sum of the parts, so let's check our options. What if the size of our original set V was 0? Well, then the total size would be 0 plus 0 plus 0, on and on forever, which is just 0. But wait, we just proved the total size has to be at least 1, so that's a contradiction. Okay, so what if the size of V was some tiny positive number? Well, if you add any positive number to itself an infinite number of times, you get infinity. But we already know the total size has to be less than 3. That's another contradiction.
We are completely boxed in. There is no way out. The only possible explanation is that our very first assumption, the idea that V even has a size to begin with, was wrong. The Vitali said V has no size. It can't be measured. It is fundamentally non-measurable. So what have we done? By accepting this one seemingly simple idea, the axiom of choice, we've proven this unmeasurable monster must exist. And in doing so, we've opened a Pandora's box of mathematical weirdness. Let's look at the even crazier things that start to happen now. And hey, you're not alone if this all feels a little strange. There's a famous saying among mathematicians from Jerry Bona that just captures the feeling perfectly. All three of those statements are logically the exact same thing, but to our brains, one feels obvious, one feels impossible, and one is just, huh? It shows just how counterintuitive this stuff can get.
And this leads us to maybe the most infamous result of them all, the Banach-Tarski paradox. It's a proven theorem that says if you accept the axiom of choice, you can take a solid sphere, break it into a few specific unmeasurable pieces, and then just by moving and rotating those pieces, reassemble them into 2 solid spheres, each one identical to the ball you started with. It's not a trick, it's a direct consequence.
I know what you're thinking. This is insane. This breaks physics. This is just too weird. Why not just get rid of the axiom of choice? Just throw it out. Then all these monsters disappear. Problem solved, right? Well, it's not quite that simple. In the 1970s, Robert Solovay actually built a consistent model of math where the axiom of choice is false. And in his world, every set of real numbers is measurable. No Vitali sets, no duplicating spheres. It seems like paradise, right? But this universe has its own snakes.
See, in a world where every set can be measured, you stumble into something just as bizarre, the division paradox. You can take the real number line, chop it up into a collection of pieces, and end up with strictly more pieces than there were points on the line you started with. How is that possible? It's just as mind-bending as anything the axiom of choice gives us.
So we're left at a crossroads. We can choose a world with unmeasurable monsters that let us duplicate matter. Or we can choose a world where a line can be cut into more pieces than it has points. It seems that when we start playing with the infinite, our intuition just completely fails us. And it forces us to ask a much deeper question. If our most fundamental rules of logic lead to these kinds of paradoxes, what does that say about the nature of mathematical reality itself?